Welcome back to Colligative Properties of Electrolyte Solutions. Now that we've reviewed our basic stoichiometry, we will now be able to calculate our Van Hoff factor of weak electrolytes. Remember our equation on our first video? I is equal to the actual number of particles in the solution after dissociation divided by the number of formula units initially dissolved in the solution. Let's use this as an example. 3 moles of weak electrolyte was dissolved in a liter of water. At equilibrium, it was found out that 1 mole of acetic acid remained, and due to impurities, only 1.8 moles of both products were harnessed. What is the Van Hoff constant of the solution? So we have your weak electrolyte acetic acid, which will produce your hydrogen ion plus your acetate. It's said that at initial there are 3 moles, and at equilibrium only 1 mole of your acetic acid remained. But your products, there are only 1.8 moles of each product. Remember our equation, I is equal to the total number of ions produced divided by the initial amount. So this will be 1.8 plus 1.8 divided by 3 moles. Therefore, our Van Hoff factor is 1.2. If this problem continued, we will be using your I is equal to 1.2 when calculating for your colligative properties of solutions. So will the colligative properties of electrolyte solution be different from the colligative properties of non-electrolyte solution? If you can remember what we studied on the first video, it said that for electrolyte solution, you will have your Van Hoff factor. Meaning, for example, we are dealing with your freezing point depression. Usually on your non-electrolyte solution, you just have your Kf multiplied with your molality. But for your electrolyte solution, it is delta Tf is equal to I, which is your Van Hoff factor, times Kf multiplied with your M. And this is also the same for your delta Tb. It will be your I times Kb times your molality. And for osmotic pressure, of course, I will also be factored. Same is true with your vapor pressure lowering. Now let's start calculating to see the difference of adding your Van Hoff factor to our equation. Let's use this as an example. 5.5 moles of a weak electrolyte was dissolved in a kilogram of phenol. It was found out that this solvent boils at 181.75 degrees Celsius with a Kb of 3.04 Celsius per molar. If the degree of dissociation of the electrolyte is 87%, what is the boiling point of the solution? So, we know that your electrolytes will dissociate to at least 2 ions. So, let's assume that our weak electrolyte will dissociate to 2 species. So, our A will dissociate to B plus C. Initially, we have 5.5 moles. And this will dissociate at 87%. Assuming that this equation is already balanced, we can say that for every 5.5 moles at 87%, we will be able to produce 4.785 moles of our B and 4.785 moles of our C. So our I would be 2 times 4.785 divided by 5.5. Our I is now equal to, it will now be equal to 1.74. The question here is, what is the boiling point of the solution? So let's write our general equation. Delta TF is equal to I KB, rather, because it's boiling point, times your molality. So delta TB is equivalent to the boiling point of solution minus the boiling point of our solvent is equal to I KB N over kilogram of solvent. So T minus 181.75 is equal to 1.74 times 3.04 times your 5.5 over 1 kilogram. What is our T, or the temperature of the boiling point of the solution? The boiling point of our solution is now 210.0928 degrees Celsius, or T is equal to 210.09 degrees Celsius. What is the freezing point of a 0.2 moles aqueous sucrose solution with a Kf of 1.86? So, since this is aqueous, therefore, the freezing point of our solvent is 0 degrees Celsius. So, let's write our equation. So, it didn't say naman na it's an electrolyte, and we are dealing with just a sugar. So, we know that this is not an electrolyte. So, we don't have to factor your I. So, Tf minus your T is equal to Kf times M. So this is 0 degrees Celsius minus T is equal to your Kf 1.86 times 0.2. Our T is now equal to negative 0.372 degrees Celsius. This is the final problem for our lecture. An electrolyte solution with a Van Hoff factor of 3 use 4 kilograms of diethyl ether. The freezing point of the solution is negative 120 degrees Celsius, with the freezing point of the solvent at negative 114.3. If the Kf of diethyl ether is 1.79 and the Kb is 2.16, what is the boiling point elevation of the solution? So how will we go about this problem? Of course, let's list down our given. I is 3. The kilograms of solvent is 4. The freezing point of our solution is negative 120 degrees Celsius. The freezing point of our solvent is negative 114.3 degrees Celsius. Our Kf is 1.79 and the Kb is 2.16. Our required, or the unknown, is the delta Tb, or our boiling point elevation. So how will we go about this if we don't have your molality? Well, first let's write the general equation of what we have, which is your freezing point. So delta Tf is equal to I times Kfm. And for delta Tb, it's I Kfm. We know that for both, you will have equal m and equal I. So let's transform our equation wherein we will be isolating m and I on one side. Now with this equation, we will be able to relate both equations for freezing point and the equation for boiling point to get our unknown. So delta TF would be divided by our KF, which is 1.79, is equal to delta TB, which is our unknown, over our KB, which is 2.60. Let me make my correction over here. So what is our delta TB? Delta TB therefore is 6.8782 degrees Celsius, or delta TB is equal to 6.88 degrees Celsius. Did you get it? I hope you did. Thank you very much for attending my class, and I will see you in the next video on solution stoichiometry.